Right. Nice to meet you, everyone. My name is Chernetsov. I work at Grammarly on the data team. And today I'm going to talking about how we built our internal data pipeline and why it's cool to do so on top of Apache Spark. And just to give you a clue on what Grammarly is, basically a cloud-based grammar, spell checking, and in general, writing enhancement tool. We live everywhere you write, for example, as a browser extension. And let's do some first analytical query today. And I need to record this. Can you raise your hand if you ever used Grammarly as a product? Well, that's a pretty good situation in the market. So let's proceed. I work Grammarly on data team. Before that, I have built analytics pipelines here and there for the last 5 years or so. And I'm a big fan of Scala and Spark recently. And let's first start with clarifying what analytics is in a consumer product company. It's basically a tool that helps to better understand who are our users, how do they interact with the product, and some details like how did they get in, how do they engage, how do they pay, how long do they stay. And all of that we need to enable everyone to make data-driven decisions. Everyone from product managers to marketing team members to engineers to support. And this is a simple picture that gives a clue of what analytics is. Basically, it takes some data about usage stats as an input and should be able to provide actionable insights in the form of reports as an output. And let's start with the right part of this and take a look at the typical reports analytics should serve. And that's the probably simplest thing you can imagine, amount of daily active users by day. The more complex example could be retention report, which allows to understand how many users still use the product after they started doing so, and split it by cohort, say, by the registration week. And this is the example we are going to be looking at throughout the presentation. Say we want to plot amount of pair conversion, so how many users bought, say, Grammarly subscription over time. But we want to slice it by traffic source those users initially came from. And to do so, we will actually need two kinds of data. First one is obviously subscription purchases. So say it's an event that fires every time somebody buys a subscription. And the second one is landing page visits, because this event contains the needed UTM tags that contain the traffic source information. So we first thing we can kind of say that, let's say everything we collect, we can generalize to certain kind of events, which would have something similar like event name and some specific dimensions for each particular event type. And in the end, we kind of obviously need to join or enrich this data, so basically pre-aggregated this data to be able to serve the reports we need. So and like quick conclusion that obviously for some reports, for the on-demand queries, these joins could be pretty hard and pretty bad in terms of how expensive they are. So we might need to join all the data we have ever collected. So it might be a good idea to do some pre-aggregations in the pipeline. So that's a picture that shows how we can split our whole analytics system into pieces. And let's start with the first one, which is capture. Actually, one more slide here. Obviously, small companies tend to start with some third-party solutions out there, and that's what we did first several years. But kind of the common conclusion is that you quickly get to the limitations, and it's getting harder and harder to achieve enough accuracy, trust, and flexibility. So let's build it. We start with the first part, which is capture. We basically have one of those events, or kind of in a form of, say, JSON blob coming in, and want to write it down somewhere. And this thing should satisfy the following requirements. It should be always up and resilient, because otherwise you might lose data, as the clients might not be able to store it while we are down. We should be able to support spikes and back pressure, which is kind kind of real-life picture, because sometimes you might have some ad campaign and a lot of users starting to come in. And you probably want to buffer this data for the delayed processing so that your pipeline after this step could have less tight requirements in terms of uptime. So that's how we did it. We built a simple REST service on top of Play framework, and it just simply writes data to Kafka, or some clients like backend tracking could directly send data to Kafka. And Kafka is great for the task. It satisfies all the requirements. And then as a next step, we'll probably want to save this data to some long-term storage for the rest of the pipeline to consume. And we use Apache Spark for that, obviously, because it's super easy to read data from almost any data source and write it to almost any other data source. And just 2 lines of code in practice. And we write data to Cassandra table as an initial primary source of truth data store. In the next step, things get much more interesting. So we enrich data, or pre-aggregated data. And we do 2 kinds of enrichment as of now. First one is so-called user attribution. In this step, we basically want to take those events we collect and enrich them with the information that allows to understand which user these events belong to. So in our example, those initial landing page visits are likely performed by a non-authenticated user. But later, when subscription is purchased, user is obviously already created an account. And so what we want to do is by matching the fingerprint, which in the web-based application case is just a cookie that lives forever on the device. I want to add this extra attributed user ID property to this non-authenticated events if we were able to infer the user ID from the other events. So in the simple case, it would look like that. Say these are the events that are coming from the same browser with the same fingerprint. User comes in as non-authenticated and creates an account and emits events with user ID there, and maybe then logs out. So gray events are non-authenticated ones, green authenticated ones. And we want to enrich this attributed user ID property to those gray events. In the more sophisticated scenario, when, say, same device is used by multiple users, we use some heuristics to attribute those events in between those several users. And so let's see how we actually implement this using Spark. Let's say we have an RD as an input that is already have data partitioned and sorted, partitioned by user and sorted by user ID and timestamp. So say this iterator contains just events from the same device sorted by time. So what we would likely do is create some buffer where we would put events till they are not while they are not having user ID as a property, so basically the non-authenticated ones. And once we see the first event with user ID, we actually take this buffer, add this attribute user ID property to each of those events, and return a trader over it as an output. So problem here is actually with this array buffer we would use, because for some outliers that emit a lot of events and never authenticate, we could have a very big set of events we have to collect and could hit out of memory exception on our worker. So instead, we would like to get into how Spark, understand better how Spark works with memory, because they are doing a similar operation while shuffle is happening. So they need to accumulate data in memory while it fits. Basically, we would also want to do so to get out of our limited, non-controlled by Spark user memory, which is by default 25% out of the whole memory your worker would have. So instead, we should use kind of an approach that Spark uses, which is to create a spillable collection, which is a collection that is able to kind of occupy managed amount of memory and spill data to disk otherwise if it didn't fit. And the logic behind how it works is the following. So the spillable collection starts with some default buffer, like default reserved memory it's allowed to occupy. You pour data in till you hit this limit. Then you would request from Spark Memory Manager an additional amount of memory. Usually you would double the amount of memory you occupy. And do so until you hit the limit, say your task and all the other tasks executed by the worker already occupy the rest of the memory. So you would go ahead and spill this data to disk and start from scratch. So in the end, you would have certain data in memory, hopefully everything if it did fit, and the rest on disk as a set of files. And you would have to be able to reconstruct your eventual collection from those two kinds of data format. And Spark has all the harness and tooling already there for you to go ahead and, say, create your own spillable collection for your needs. So first, you would use this size tracker trait, which allows to estimate the size of JVM heap, basically size of the object in JVM heap, and it supports kind of satisfies all the performance requirements you would have, such as very quickly updating the internal counters basically on every update, and from time to time performing the kind of the full hierarchical scan to do the estimate, and extrapolates every other time you request size. Then you would use the spillable trait to wrap kind of the whole collection, and there you would find this maybe spill method that is automatically talking to Spark task memory manager to request 2 times more memory each time you hit the limit. And you should just implement a spill method to write the data to disk if you already have hit the limit. And here are those 2 methods that this class would call in this tasks memory manager that you can have access to using your Spark task context. So in the end, this approach allows you to be safe with outliers when you process kind of potentially unlimited or like not fitting in memory amounts of data in your task code. You can benefit from the whole memory you have instead of the smaller portion you usually have in your user space. And yeah, like small comment, I think these APIs are not very published in Spark documentation, but they could be, which would probably encourage more people to do so. Second kind of enrichment we do is so-called calculable properties, which is basically an idea that allows to define what kind of pre-aggregation you want to do and which kind of extra dimension as a result of that you want to add to each event. So in this case, we would likely want to add an extra dimension to each of the subscribe event that would have the information about the first UTM medium page visit that happened prior to the subscribe event. And how we did that is we created a fancy functional Scala DSL to describe those transformations. And here's how it looks. But the main requirements it satisfies is it's type safe and functional and composable, which makes it kind of friendly from developer's standpoint to build those, to define those aggregations. It's pretty similar to Scala Collections API, and it works in batch and stream mode. And basically, for streaming mode, we need it to be incremental, which is not requiring to pull a lot of data from long-term storage as the new data comes in to enrich common events incrementally. Sorry. Let's figure out how do we actually go ahead and kind of build this whole pipeline that will kind of perform several steps of enrichment as we go. So we already saw this picture where we just save data to some long-term storage taking it from Kafka. As a next step, we would probably want to write data to some next Kafka and read it from there in order to perform user attribution. And like for the long-term use, we also write it to some long-term storage, which is now, in our case, one more Cassandra table. And similarly, we would do the third transformation by sending those attribute events, user attribute events to one more Kafka and reading it from there to perform enrichment with calculable properties and eventually write it to some queryable index. And because we would want to change our mind about how we do this enrichment for all the historical data we have collected, we would probably want to have the batch mode for each of those steps so we could recompute the whole data in some new form. So obviously we use Spark for all of that. For streaming, we use microbatch and like normal big batch jobs for batch mode. And of course, we reuse a lot of code between those two modes. And let's take a little deeper look into one of the, a few notes here. So Spark is great for that because it has connectors for everything. Obviously, it's great for batch because it supports kind of shuffle with speeding. So when you have data much more than fits in memory, you'll actually be able to process it. It can failure recovery. It has failure recovery, which is critical for long-running jobs. You don't want it to fail. Instead, you want some retry to happen and the job to proceed. And great for streaming because fast with literally no overhead, so you can launch those micro batches very often. And let's take a little bit deeper look into this portion of the picture where we actually, as it turns out, want to read data from some source and write it to multiple destinations, which in this case could be like a couple of Cassandra tables and Kafka topic. So how do we do that actually in the form of Spark, in terms of Spark code? We would have some RDDs in input. And as a first try, let's actually just one after another write this RDD to several data stores. So like those three, like here. What will this actually look like if you drill deeper into, say, one of these writer codes? It's actually usually launched in the for each partition on the RD APIs, which eventually causes a new Spark job to start. And as a result, instead of having a single job that would actually write to all three destinations at once, we'll actually have three jobs that would, each of them would have to read data from this Kafka topic as it runs, which is probably not the best thing. Probably, like for streaming, it's kind of fine, but for batch job, you really don't want to read your data 3 times before you write it to your destinations. So let's do another try. Let's first cache our RDD and see how it goes after that. It turns out we are still going to have 3 jobs, but the other 2 will try to read data from cache if it did fit there, which is, again, probably not the optimal solution. So what we decided to do instead is we wanted to dive deeper into how these writers work, understand how we can tweak those in order to do what we want. So the typical writer, say in this case, which simply writes data to some file, would look like this. Kind of in this case, we'll just create a file output stream, and in each partition, I would just write each element to the writer and close it. So obviously, these writers have to satisfy certain requirements, like being able to buffer data, not to congest kind of the whole processing, so be non-blocking, and handle the cases when we have to retry. So either the storage has to be idempotent, or we should be able to somehow override, like this already written bits of data, like in the file case, we should just kind of override the file from scratch. And what we did is basically we came up with this end writer approach, basically, which instead of map partitions, or instead of for each partition would do map partitions, and would create this same writer, and instead of doing like for each on the iterator, would do map and write each element there. And we would have to do some tricks to be able to save this, to close this writer once the iterator is done. So with this approach, we were able to achieve our goal. We had to kind of basically build an extra bits of code for all the connectors we use, like Spark Cassandra connector, Kafka connector, and Hadoop writer. And it allowed us to make those pipeline steps, which involve writing to multiple destinations, much more efficient. Cool. So the third part I wanted to touch is how we actually index data, which is how do we put it in some form which is efficiently queryable. And I'm not going to be able to dive deeper there because I don't have an indefinite time. I'll just touch on the main aspects, and we'll be happy to discuss it afterwards. Basically, we write data, we store data as a set of Parquet files on top of S3, but we don't use the kind of built-in Hive partitioning. We use a custom one where we split data by event name and time intervals, and dynamically based on rate of events for each of the event type. And to enable kind of absurd or updating already existing events, we perform some kind of appending data and separate asynchronous compaction process, and are able to merge the data on the fly when querying. And we use some tricks to make the work with S3, AWS S3 efficient. For example, achieve the read after write consistency, or randomize names to maximize parallelism. And few stats, we have thousands of events per second as of now, and several terabytes of compressed data accumulated so far. Probably it's not the scale of these huge companies yet, but we are slowly getting there. And the last piece I wanted to cover is how we do querying. So typically, you would kind of see the setup where there is a data scientist team that would go use, say in this case, Spark API to work with data frames, or just pure SQL to write those reports and expose it into some in some UIs, for example, using Zeppelin. But we also found that it's critical to have some casual way of reporting where non-technical people or even technical could do these things much easier. And here's an example of a simple report, maybe simplest possible report this casual querying should support, which is basically want to plot certain event by day, want to filter it, count maybe unique visitors instead of counting the whole total number of events, filter by certain dimension, split by certain other dimension, and pick the time interval. So it turns out even this kind of query gets pretty complex as you add features, several kind of tens or hundreds lines of code. And the other approach you could take is actually try building those UIs that would allow you to configure those queries. But turns out it's kind of pretty expensive, especially for in-house product like ours. So what we did instead is we decided to go with custom query language, which would take all the benefits SQL has, like flexibility it provides, but be very much tailored to the kinds of reporting we typically do and cover this casual querying use case. So that's how our segment query would typically look like. And we do it actually by, in a lot of sense, reusing what Spark already has for its Spark SQL functionality. So we basically take the existing Spark parser to parse the most complex piece, which is expressions, which are mostly the ones that will be customized by end user. And using this custom query language approach, we have so far implemented certain types of reporting, like segment, funnel, or retention analysis reports. We use this to both interact with data in Zeppelin and in our custom small UI for that. One more trick about building your query language on top of Spark parser for SQL is that they had it implemented using Spark parser combinators until version 1.6. Unfortunately, or like fortunately, I don't know, starting Spark 2.0, they have it implemented using NTLR, which is much harder to extend. But you can always kind of take it from there and backport it for 2.0. And yeah, it turns out it's kind of very, not that hard, and becomes very extensible, so it's very easy to and cheap to add more features to a query language to satisfy your customer needs. And one more bonus you get from having your custom parser for your custom language is that you can go ahead and improve indefinitely the user experience. Say this query UI, where you would write your queries, like provide syntax highlighting and even schema exploration capabilities. We basically have our own set of specifications for the data that's being tracked, and we're able to, like in a context-aware fashion, understand what type of, what part of the query user is entering, and provide autocomplete functionality that allows exploring what kinds of dimensions certain events have. So few bits to conclude my talk. It turns out that building a custom versatile analytics is doable and enjoyable. Spark is an awesome platform for that. Go ahead and do it. It supports all the use cases we could think of, both the pipeline case where you need to enrich data in a streaming and batch fashion, and querying and machine learning is the next step for us. And one more thing that maybe is not that obvious to Spark maintainers or the community would be cool to have deeper insights, more friendly, because I think it's the biggest feature of Spark that it's so extensible. I think that could bring a lot more innovation in the industry. We are obviously hiring in every possible team in the company and data team as well. So reach to me if you're interested. And I'm ready to answer your questions. I think we have a couple of more minutes for that.
Yeah, so if you have any questions, feel free to come up and ask them at the microphones on the left to right side of the room.
I saw that you said the scalable function, is that provided by Spark, or you have a customized implementation for that, the memory thing? You mentioned that if we go out of the executor memory, you want to put some data on the disk. That part, can you explain more? Like, do you have any customized solution for that?
Yeah, so probably you're talking about, sorry. So this part, right? So
yeah,
scalable data.
Yeah, I mean, just I never use that, so that.
Yeah, so not sure I got all the parts of your question, but basically all these bits of kind of code I was showing, which is the spillable trait, size tracker, and the interface, how task memory manager looks, is kind of all available and is being used by Spark's own collections. Spark own collection that they use for shuffle, for example, when they do on-disk sort. And if you would want to come up with your own spillable collection, you would have to like mostly implement your own business logic that you need in this collection, and many of those things like estimating size you occupy in memory, writing it to a file on disk, like allocating, creating new like random file path on disk and so on, it would be already available there for you as a kind of inside Spark code base.
Yeah, I mean, I think we have the like serialized to memory or to memory at disk for the data. So I'm just not quite sure why we still need the spillable function to make sure the memory doesn't go out of the executor. But yeah.
Don't think I got a question.
Yeah, we can talk offline.
Let's discuss after the talk.
Cool. If there are no more questions, let's give Misha one more round of applause.